Hello, and welcome to the next installment of Introduction to Computer Graphics. I am Patrick Curran. Computer graphics can be anything like images of a mountain, an automobile, trees, animals, or anything else we can imagine. These images are made up of the most basic components called graphics output primitives, or simply primitives. Output primitives are geometric structures like points, straight line segments, circles, conic sections, quadratic surfaces, spline curves and surfaces, polygon color areas, and character strings. To describe a picture, we first decide on a convenient Cartesian coordinate system. This is called the world coordinate reference frame, which could either be two-dimensional or three-dimensional. We then describe the objects in our picture by giving their geometric specifications in terms of positions in world coordinates. For instance, we define a straight line segment with two endpoint positions, and a polygon is specified with a set of positions for its vertices. These coordinate positions are stored in the scene description along with other information about the objects, such as their color and their coordinate extents. A set of coordinate extents is also known as the bounding box for an object. The set describes the minimum and maximum x and y and z values for each object. For a two-dimensional figure, the coordinate extents are sometimes called the object's bounding rectangle. Locations on a monitor are referenced in integer screen coordinates, which correspond to pixel positions in the frame buffer. Pixel coordinate values give the scanline numbers, the y value, and the column number, the x value, along the scanline. Hardware processes such as screen refreshing typically address pixel positions with respects to the top left corner of the screen. Scanlines are then referenced from 0 at the top of the screen to some integer value, y max, at the bottom of the screen, and pixel positions along each scanline are numbered from 0 to x max, left to right. Next, we will talk about programming points and lines. To specify the geometry of a point, we simply give a coordinate position in the world reference frame to the OpenGL function glVertex to state the coordinate values for a single position. The asterisk indicates the suffix codes that are required for the function. These suffix codes are used to identify the spatial dimension and the numerical data type to be used for the coordinate values. The glVertex function must be placed between a glBegin function and a glEnd function, like so. The argument of the glBegin function is used to identify the kind of output primitive that is to be displayed, and the glEnd function takes no argument. For plot pointing, the argument of the glBegin function is the symbolic constant glPoints. In the following example, 3 equally spaced points are plotted along a two-dimensional straight line path with a slope of 2. Coordinates are given as integer pairs. To create a line in OpenGL, we select a single endpoint coordinate position using the glVertex function, just as we did for a point position. Then we enclose a list of glVertex functions between the glBegin and glEnd pair. But now we use the symbolic constant as the argument for the glBegin function that interprets a list of positions as the endpoint coordinates for line segments. There are 3 symbolic constants in OpenGL that we can use to specify how a list of endpoint positions should be connected to form a set of straight line segments. They are glLines, glLineStrip, glLineLoop. Here, a set of straight line segments between each successive pair of endpoints in a list is generated using the primitive line constant glLines. Here we can see this will result in a set of unconnected lines unless some coordinate positions are repeated. Nothing is displayed if only one endpoint is specified, and the last endpoint is not processed if the number of endpoints listed is odd. For example, if we have 5 coordinate positions labeled P1 through P5, and each is represented as a two-dimensional array, then the following code would generate this. With GL line strip, we obtain a polyline. In this case, the display is a sequence of connected line segments between the first endpoint in the list and the last endpoint. Using the same 5 coordinate positions as in the previous example, we obtain this. Using the third line primitive GL line loop, we get a closed polyline. An additional line is added to the line sequence from the previous example, so that the last coordinate endpoint in the sequence is connected to the first coordinate endpoint of the polyline, resulting in this. Now let's turn our attention to line drawing algorithms. Drawing lines in computer graphics is a fundamental skill, but is more challenging than putting pencil to paper. To display a line, the graphic system must first project the endpoints to screen coordinates and determine the nearest pixel positions along the line path between the endpoints. Next, we will talk about the math behind a simple line drawing algorithm. We can determine the path of a line using the geometric properties from the slope equation, where m is the slope and b is the y-intercept, which are defined as follows. For any given x interval, or delta x, along a line, we can compute the corresponding y interval, or delta y, using this equation. Likewise, we can obtain the x interval, or delta x, corresponding to a specified y interval, or delta y, using this equation. Now let's discuss the Digital Difference Analyzer, or DDA. It is a scan conversion line algorithm based on calculating either delta x or delta y using these equations respectively. Here is the pseudocode. As you can see, it is relatively simple, defining several variables, a conditional statement to evaluate if delta x is larger than delta y, and then a for loop to increment through x and y values and turning on the corresponding pixel values. Next, we will look at a second line drawing algorithm called Bressingham's algorithm. Consider a line with initial point x1, y1 and a terminal point x2, y2. Using an example like this, where we want to draw a line from point 0, 0 to 5, 3, if we start with a pixel in the 0, 0 position, how do we choose which pixel to use next? Here or here? Bressingham's algorithm provides a mathematical determination of which position to choose between 2 points that will emulate a straight line. It is an accurate and efficient line generating algorithm that uses only incremental integer calculations. The algorithm can be adapted to display circles and curves as well. First, we calculate the delta x component of each point and the delta y component of each point. Next, we calculate the slope using delta y over delta x. If delta x is greater than or equal to delta y, then the x-axis will be the driving axis. Otherwise, if delta y is greater than delta x, the y-axis will be the driving axis. The driving axis is used as the axis of control for the algorithm. Here is an example using Bressingham's algorithm. We want to draw a line from 0, 0 to 5, 3. We start by turning on the pixel in position 0, 0. Then the algorithm tells us to turn on pixel 1, 0. Next, the algorithm tells us to turn on pixel 2, 1. After which, we turn on pixel 3, 1. And finally, we turn on pixel 4, 2. Hardware processes such as screen refreshing typically address pixel positions with respect to the top left corner of the screen. Scan lines are then referenced from 0 at the top of the screen to some integer value, y max, at the bottom of the screen, and pixel positions along each scan line are numbered from 0 to x max, left to right. However, with software commands, we can set up any convenient reference frame for screen positions. For example, we could specify an integer range for screen positions with the coordinate origin at the lower left of the screen area. Line clipping is when the line extends beyond the window, like so. Generally, Any procedure that eliminates those portions of a picture that are either inside or outside a specified region of space is referred to as a clipping algorithm, or simply clipping. Usually, a clipping region is a rectangle in standard position, although we could use any shape for a clipping application. Clipping algorithms are applied in two-dimensional viewing procedures to identify those parts of the picture that are within the clipping window. Everything outside the clipping window is then eliminated from the scene description that is transferred to the output device. Now let's talk about circle algorithms. One of Archimedes' most important achievements was the method of approximating the area of the unit circle using inscribed and circumscribed polygons, known as the classical method of exhaustion. Archimedes realized that the area of a regular polygon of n sides inscribed in a unit circle is smaller than the area of the circle, which in turn is smaller than the area of a regular polygon of n sides circumscribed about the circle. As n approaches infinity, the two polygonal areas should approach the area of the unit circle. Circle algorithms via implicit functions is what we'll talk about next. We can describe a circle with the relation x squared plus y squared equals 1. The natural thing to do is to solve for y. The function y equals x squared plus 2x plus 1 that we found by solving for y is called the implicit function of the relation. Bressingham's algorithm that we discussed earlier in this presentation was later extended to produce circles. The resulting algorithm is sometimes known as either Bressingham's circle algorithm or midpoint circle algorithm. It is used to determine the points needed to rasterize a circle. The algorithm can be generalized to conic sections. This algorithm draws all 8 octants simultaneously. In a concave polygon, a line segment connecting any 2 points may or may not lie inside the polygon. In convex polygons, any line segment adjoining any 2 inside points lies inside the polygon. Once we have identified a concave polygon, we can split it into a set of convex polygons. This can be accomplished using edge vectors and edge cross products. Or we can use vector positions relative to an edge extension line to determine which vertices are on one side of this line and which are on the other. To split a convex polygon, To split a convex polygon, we make a list of its vertices to transform it into a set of triangles. This can be accomplished by first defining any sequence of 3 consecutive vertices to be a new polygon, a triangle. The middle triangle vertex is then deleted from the original vertex list. Then the same procedure is applied to this modified vertex list to strip off another triangle. We continue forming triangles in this manner until the original polygon is reduced to just 3 vertices. Thank you for watching this presentation. I hope that you found it informative.